I'm going to show you how to use an ICE table and how to calculate the equilibrium constant using ICE tables. So thus far we learned that equilibrium is the rate of the forward reaction is equal to the rate of the reverse reaction, and you can set up a K-eq equation and calculate it. And then if you want to manipulate the reaction, you would use one of Le Chatelier's principles. And we're going to kind of circle around, and I'm going to show you another way to calculate the equilibrium constant if you don't have all of the variables. And that's what an ICE table is for. So the first problem, or the first example, I'm going to give you two examples, is the initial concentration of COCl2 gas is 0.0350 molar. And the equilibrium concentration of carbon monoxide gas is equal to 0.0232 molar. Calculate the K EQ of this reaction. So the first thing we need is a balanced chemical equation. So this is a decomposition reaction where this compound or this reactant breaks apart into two products, carbon monoxide gas and chlorine gas. So this is 1 mole decomposing into 1 mole of carbon monoxide gas and 1 mole of chlorine gas. And that's really important. So an ICE table is a rectangular box broken up into 3 rows, like this. So the 3 rows represent the ICE. So ICE stands for initial concentration, that's what the I is. The change in concentration, which is the C. And then the E stands for the end point, which is the end when equilibrium has been reached. So end/equilibrium. Okay. The amount of columns that you use is dependent on the equation. So because I have 3 species in this reaction, I have 1 reactant and 2 products, I'm going to get 3 columns. If there were 4 species in the reaction, I would have 4 columns. So then I'm going to rewrite the reaction on top of the ICE table and designate each column as one of the species. Now that I have each column designated one of the species in the reaction, I can start the process. So back up to the problem, it says the initial concentration of COCl2 gas is 0.0350 molar. So I'm going to go to the initial row and to the compound and fill in that value, 0.0350 molar. Just a note, you notice I wrote the word concentration over and over again. A value cannot go in here at this point if it's not in a molarity concentration. So if I give you moles and liters in a problem, you would have to convert that to molarity, knowing that molarity equals moles divided by liters. So that's something that you may have to do in problems that you see. All right. What else is in the problem? It says the equilibrium concentration of carbon monoxide gas is 0.0232, and because it says at equilibrium, I need to go down to my end line, find that compound, and then put that value in that box. Okay, if I have a chemical reaction at the very, very beginning, at the genesis of the reaction at time 0, I don't have any products because the reaction hasn't started. And so you can assume the initial concentration before the reaction proceeds for the products are going to be 0. So the product initial concentrations are always 0 in this context. All right, so now we have our entire top row filled out. Let's talk about change. The change is how much am I losing from my reactants and how much am I gaining to the product as the reaction proceeds towards equilibrium. Well, we use the letter X to denote what's being lost and what's being gained. and a plus or minus symbol to show loss or gain. So if my reactants are turning into product, I'm losing reactant and I'm losing X amount. My products are CO and Cl2, which means over time I'm going to add on product. So my change is minus X plus X plus X. There we go, that's better. Okay, so now this chart is almost completely filled out. One of these columns is going to determine the value of X. So this column right here is completely filled out, so that's the column that I want to look at. So this is showing that 0 plus X equals 0.0232 molar. So I can make the assumption that X equals 0.0232. And I can also make the assumption if this is 0 plus X, it would equal the same thing. So the concentrations, because this is a 1-to-1 mole ratio, are going to be equal at equilibrium. All right, so then back over to this column, in order to figure out the equilibrium or ending point concentration of my reactant, I need to take the initial concentration minus the change and then find the end concentration. And so on my calculator, I'm going to take the initial concentration, 0.0350, and subtract 0.0232. I get 0.0118. So 0.0118. Again, I just took the initial minus what X equals, minus X, and that equals my ending equilibrium concentration of my reactant. So now that I have all of these three values, I can set up a KEQ equation. So KEQ equals product divided by the reactant. In this case, I have two products, carbon monoxide, chlorine gas, and I have this one product. So there are no coefficients, so they're all to the power of 1, and then I just plug in the numbers. So I have carbon monoxide 0.0232 multiplied by the same value because those are equal at equilibrium, and then divide by 0.0118. These numerators, 0.0232 times 0.0232, is the same thing as saying 0.0232 squared. And so that's what I'll do in the calculator. So it's 0.0232 squared equals, and then divide by my denominator, 0.0118. And I get a KEQ of 0.0456. And if you remember, KEQs less than 1 favor reactants. Okay, so that's the first problem. The second problem, I'm just going to use generic letters instead of an actual equation. So let's say the equation is 2A plus B produces C plus 2D. It's the exact same concept, but only slightly more complicated. So let's just list out initial concentrations of A and B equals 0.45 molar and 0.31 molar. And the equilibrium concentration of C equals 0.12 molar. Okay, so I'm going to set up my ice table. And set up the ice with 3 columns, or 3 rows, I'm sorry, 3 rows. So initial change and then the end equilibrium point, and I'm going to letter, I have 2A plus B, C plus 2D, which means I need 4 columns, 1 for each letter. Okay, So in this situation, I actually have coefficients, which is going to change the middle row or the change row. And I'll show you what that looks like in just a minute after I fill out all of these values. So it says I have an initial concentration of A, 0.45 molar, an initial concentration of B, 0.31 molar, and an equilibrium concentration for C of 0.12 molar. All right, I don't have anything else at this point. And again, we can assume at the very, very start of the reaction, like time 0, we have no concentration of product. So it's 0, 0. All right, so let's talk about the change. If this says that 2 moles of A is combined with 1 mole of B to produce 1 mole of C and 2 moles of D, I need to account for that in the change. So my reactants are going to subtract X and my products are going to add X. However, it's actually for this reaction specifically minus 2X because it's 2A, minus X because it's 1B, plus X because it's just 1 mole of C, and plus 2X because it's 2 moles of D. So the coefficients are represented in the change here. And then to find my ending equilibrium values, well, this row right here tells me what X equals. 0 plus X equals 0.12, therefore X equals 0.12. So over here, if I know that X equals 0.12, then 2 times that is going to be 0.24. So it'll be double the concentration. So coming over to B, if I know that X equals 0.12, then I can take the initial concentration, which is 0.31, minus what X equals, which is 0.12, and that gets me a concentration of 0.19 molar. And because this is minus 2X, I know that I have to use double, which is going to be 0.24, so I'm going to take 0.45 minus 0.24 because that's double X, and I get the concentration 0.21 molar. All right, so now I can solve KEQ, and it's going to equal concentration of C multiplied by the concentration of D to the second power, because that 2 right there, divided by the concentration of A to the second power multiplied by the concentration of B to the first. I can plug in my values, so C is 0.12, D is 0.24 to the second, A is 0.21 to the second, and then B is 0.19 to the first. All right, so then in the calculator, I'm going to take care of the denominator first. So I have 0.21 squared equals times 0.19 equals. Write that out. 0.008379. Please don't round these numbers. You can only round final answers. This is not a final answer. All right, and then my numerator is 0.24 squared times 0.12, and that goes up top, 0.006912. And then I divide by my denominator, 0.008379, gets me 0.82. So KEQ equals 0.82, which is a K less than 1, therefore it favors reactants.